An important step to conceptualize microbial growth is to sketch metabolisms. So let's go on. Here we will shortly recall the concept of black box growth analysis. We will look at some examples of good or weak electron donors and electron acceptors, as well as efficient or less efficient carbon and nitrogen sources. This will provide us the basis to sketch the growth system of an organism. These conceptual models will be applied to predict the growth of microbial guilds of wastewater treatment plants. Considering sludge and microorganisms as black boxes is perfectly fine for designing and operating wastewater treatment plants. Nonetheless, it is important to get insights on what happens outside the cells. One should measure electron donors and electron acceptors needed for catabolisms in red, and carbon and nitrogen sources that are assimilated in the biomass in green. A good listing of them is always useful to characterize your microorganisms of interest. This table illustrates examples of carbon and nitrogen sources on the left and electron donors and acceptors on the right. Reduced compounds like acetate or glucose are good carbon sources. They are already in a reduction state close to biomass. The degree of reduction is the amount of electrons contained in a substrate. Carbon dioxide or bicarbonate can be used by autotrophic microorganisms to form their biomass, but they are much more oxidized and will need more electron resources to get lifted up toward the reduction state of biomass. Therefore, the growth of autotrophs is less efficient than heterotrophs. Ammonium is an excellent nitrogen source since already in the reduction state of amino acids and proteins. Etymologically, you can already detect that ammonium and amino acids are quite close in their chemical formula. Nitrite and nitrate can be used as nitrogen sources, but they are oxidized and will require an electron input to lift them up to the state of amino acids. In addition, these nitrogen oxides also act as electron acceptors. They are not always welcome in some tanks of wastewater treatment plants that need to say anaerobic or fermentative for the microbiologist. They will disturb the fermentation process or substrate storage by PAOs. Reduced compounds like many organics, H2 and H2S, are very good electron donors. Ammonium can also donate electrons, but it is a weak electron donor based on its Gibbs free energy change per electron. Water is also an electron donor, but mainly only phototrophs are able to get the electrons from it by splitting water using energy from light. Dissolved oxygen is an electron acceptor, an excellent one. Nitrogen oxides, iron 2 and sulfate are good ones too. Carbon dioxide can be an electron acceptor, but weaker. It is used for both some anabolisms, for autotrophy, and catabolisms. Notably, methane is produced by hydrogenotrophic methanogens through the reduction of CO2 by H2. Thus, based on the combinations of these different E donors and E acceptors, as well as carbon and nitrogen source, you can start to explore and analyze the microbial and metabolic diversity in activated sludge. This table is a recall on the growth systems of the main guilds of BNR processes in wastewater treatment plants. Please remind to duly list the carbon and nitrogen sources for the anabolism and the electron donor couple and electron acceptor couple for the catabolism. Such list is important to further conceptualize their growth and highlight their interactions. By using the information of the previous table, you can now easily sketch the metabolisms of your preferred microorganisms. Such imprint provides an efficient visualized information of the main exogenous resources needed for each microorganism to grow and how they are converted. The metabolic functionalities of an organism are coded on its genome, displayed here in the center. But it is far enough to consider microbial growth with the carbon and nitrogen sources and electron donors and electron acceptors that are needed for its metabolism. You can use such sketch in any microbiological, biotechnological, or environmental engineering work involving microorganisms. Just take a pencil and a sheet of paper and sketch your preferred metabolisms. You can, for instance, try that for heterotrophs, nitrifiers, denitrifiers, or fermenters. Please pause your video and we'll join for the solutions. These are metabolic examples that I sketched for heterotrophs in red, nitrifiers in light blue, here resembling a COMAMOX metabolism from ammonium to nitrate, denitrifiers, and fermenters. Heterotrophs use acetate as carbon source and electron donor, ammonium as nitrogen source, and oxygen as electron acceptors. Nitrifiers use here ammonium as electron donor and nitrogen source, oxygen as electron acceptor, and bicarbonate, either CO2 as pH 7, as carbon source. Denitrifiers, for instance, use acetate as carbon source and electron donor, nitrate as nitrogen source and electron acceptors. Fermenters ferment glucose into a fermentation product like acetate and ethanol. They use this glucose as carbon source for biomass growth together with ammonium as nitrogen source. These schemes provide a very clear picture of the resources needed by each of these microorganisms to grow. You can also see that several compounds can be used for different anabolic and catabolic purposes simultaneously. In addition, you can start conceptualizing sludge as an ecosystem of interacting microorganisms by connecting the dots. You can look at their competitions for substrate as well as their metabolic interdependencies. Different organisms compete for the same resource. Heterotrophs and denitrifiers for the electron donors and carbon source. Heterotrophs and nitrifiers for the electron acceptor, oxygen, and the nitrogen source, ammonium. Fermenters produce acetate by fermenting glucose. This acetate can be used by heterotrophs and denitrifiers in their growth. The CO2 that is produced by heterotrophs, denitrifiers, and fermenters can be used by nitrifiers to grow. Nitrifiers produce nitrate by converting ammonium. This nitrate can be used as electron acceptor by denitrifiers. These are additional sketches that you can find in the chapter 2 of the examples and exercise book. You will find some sketches for heterotrophs, the different types of nitrifiers, denitrifiers, and anamox organisms. The metabolic sketches of wastewater treatment plant microorganisms can further help you identify which conditions are needed to be applied in the sludge tanks to select for each microbial guild and where to position each tank and redox condition in the flow scheme depending on the availability of substrate that flow with the wastewater and the mixed liquor. In an anaxic aerobic system, AO system, denitrifiers are positioned in the first tank where they obtain the organic matter as electron donor and carbon source. They receive the electron acceptor by recirculating the nitrate that is produced during nitrification. After the denitrification, an aeration tank is operated by sparging air to provide the electron acceptors for nitrifiers to convert ammonium into nitrite and nitrate. In this aerated zone, nitrifiers are active, like ammonium oxidizers, nitrite oxidizers, or COMAMOX organisms. The CO2 or bicarbonate that is produced by the denitrifiers first will be used as carbon source by the nitrifiers. It also acts as alkalinity to buffer the acidity produced by nitrification. Similar critical thinking can be done on the establishment of these microbial guilds across the gradient of substrates that are generated by diffusion limitation in the deepness of a biofilm or a granule. To conclude, a well-defined growth system provides a clear understanding of the metabolism of any microorganism. Just list the carbon and nitrogen sources, the electron donor couple and electron acceptor couple. These simple sketches of growth components are efficient to address microbial interactions. Microorganisms can metabolize a range of good or weak substrates, delivering different growth performances. you should now be able to further dig into the black box growth analysis from listing and sketches of the growth system to stoichiometric, thermodynamic, and kinetic formulations that you will address in the next part of this course.